Hello, Tamil sir. Hello, hello.
you want to build a house. What is the building block of building a house? That is a brick. आप fundamentally क्या होता है? Brick मतलब
Hello, sir. Good evening, sir.
Sir, good evening.
How are you, sir?
Fine, thank you.
Do you hear me, sir?
Yeah, I'm able to
My
hear.
voice clear?
Are you able to hear
Yes,
my
sir.
voice,
Yes.
sir? Yeah, very
Let me
clear.
try to share my screen.
Okay.
Screen is also visible, right, sir?
Uh, no, sir. I'm not able to see.
Now, sir?
Yeah,
Oh, okay, sir.
fine.
Let me stop sharing the screen. Mute my video. Once you start, I will switch on my mic and video, sir.
Yeah. Sir, I think few more minutes. I think the participants are yet to join. So we shall start by 6:30 to 35 between that. So once it reaches maximum more than 75, we will start, sir.
Sure, sir. Okay, sir.
Okay. I think we shall start, sir.
Yes, sir. I'm ready.
Yeah. Yeah. I would like to invite you formally. So the resource person of today's program, my beloved Karthiganesh Durai, and my dear participants. Very good evening to one and all join in today's online session. It actually gives me immense pleasure to welcome you all for day three session of our 6-day faculty development program, Emerging Trends in Quantum Technologies. As we progress deeper into simulating journey today, I think today's session will be more interesting. I think it will be promising. It is indeed to great honor to welcome our distinguished resource person for today's Mr. Karthiganesh Durai. He is an accomplished entrepreneur and quantum computing architect, professor of statistics and data scientist based in Bangalore. Mr. Karthiganesh Durai is a versatile technologist whose expertise beautifully integrates quantum computing, data science, business intelligence, and software architecture. His hands-on experience with QisKit and quantum machine learning position him at a perfect applied quantum researcher, and beyond quantum technologies, he is a seasoned data scientist and Python expert with extensive experience in big data, Teradata, or SharePoint, Power BI, and Excel VBA and MS project. His professional contributions are truly commendable, and he developed mark-to-mark based solutions for a Singapore-based supply chain organization and built knowledge management system for leading Singapore shipyard, and designed high-end server costing analyticals double sound solutions using Excel VBA and Power BI, and created an SLA compliance production system using Python, showcasing predictive analytics excellence, and contributed to data engineering solutions for Celonis process mining. And his interdisciplinary approach perfectly aligns with the objective of FDPs today, and integrate quantum computing algorithms, quantum machine learning, and real-world applications. So, on behalf of the Department of AIDs, I extend our heartfelt welcome, sir. We are truly grateful for your time and willingness to share your expertise with us. I'm confident that today's session will be highly insightful for all the participants, as you are going to learn the hands-on simulation using QisKit. With a great pleasure, I now invite Mr. Karthiganesh Durai to take over the session. Thank you, sir.
Thanks for the nice introduction, sir. I realize you collected a lot of detail about me. You're telling more than what I remember.
Yes, sir. Really, thank you so much for accepting.
Thanks a lot, sir. So,
yes, sir.
Let us start the session.
Yeah.
As the introduction was very elaborate, we're directly jumping into the quantum computing hands-on session. So when many people are talking about the quantum computing and hands-on session, the first tool what comes to our mind is IBM QisKit. And you are not alone. Everyone who are starting, they start with IBM QisKit only. But when I started my career in quantum computing, my first project was in 2010 on implementing quantum algorithm. That time IBM QisKit was not there. So I did on a language called quantum computing language, a C++ variant. I started from there. That's why my understanding on quantum computing is something from the how to say C++ oriented simulator. But that helps a lot. So with that introduction, let me start the session. Theory will come whenever required. Most of the time we are working on Google Colab. So I request all of you fire up your Google Colab. Go to colab.research.google.com. I believe most of you will have that activated in your account. Go there and let me paste the URL for your benefit, such that it will be easy for you to, if to just click the link and open that one. And here I already created a new, I will close this one, okay? And I close this Gemini AI also, and I have it. So this is my screen. So the Google Notebook will not have any IBM QisKit installed. So we have to start with these 4 pip install. Pip install, let me zoom it, okay? Pip install QisKit, pip install QisKit -AER, pip install matplotlib, pip install PyLatex ENC. These are the 4 packages you need, so please install them. I am pasting these things also into the chat window such that you need not to spend time, directly work on this one. Just to copy paste in your Google Notebook, it will be ready. It will take some 1 to 2 minutes. So I am storing 0 to 11 SRM. So it is collecting and installing. It will take that. It's a sweet time. Hopefully, yes, successfully built by, yeah, everything is completed now. Now my package is ready, meaning that my notebook is ready to implement some simple QisKit program. Here I have a question. If anyone asks you to build a QisKit program, do you think, oh, I don't know the syntax, so I have to search in online or IBM QisKit documentation from their Control-C, Control-V? 80% of the beginners are in that stage only, nothing wrong in it. But in today's session, I'm going to give you the confidence. It's not necessary. We can type a quantum program from our memory also. You can understand how it is much easier than searching Control-C, Control-V. Of course, you have to remember the syntaxes. For that, it may take 1 or 2 months for you to learn those things. But today's session will be the first step for typing quantum programs from our memory. Try to follow that approach. I'm creating another code. There are 4 steps in the workflow. In a workflow, there are 4 steps. Workflow has 4 steps. First step is designing a circuit. Second step is executing the circuit in simulator or real QPU. Third step is visualizing output. Fourth step is interpreting output. These are the 4 steps. So first step, I am going to design a circuit. So for designing a circuit, instead of selecting a complicated circuit, I am selecting a random circuit, single qubit. Okay. Can I proceed? I believe all of you have installed the pip install. So I am creating from QisKit import quantum register, classical register, quantum circuit. These are the 3 things I need. And also I need to show the image from matplotlib, import pyplot as PLT. So these 2 import statements are necessary for designing the circuit. Let me paste this in your chat window so you can copy paste. Now coming back to the code, now I imported, I'm going to create a quantum register with a single qubit. So quantum register 1, this 1 indicates single qubit. So number of qubits should be the first parameter. It is suggesting I don't want to accept that the letter Q is anything. You can give any letter to identify the quantum register. CR equal to classical register with 1 qubit. Mostly the number of qubit and number of bit will be same. So the name also I'm giving. And now I have created, I don't want to use this one, QC equal to, okay, let us use the word circuit, because that is circuit equal to quantum circuit. This circuit should be created using QR comma CR. Now in this circuit I am going to add quantum gates. So circuit dot X gate QR of 0 and circuit of Y gate of QR of 0, sorry, QR of 0. I believe all of you are following along with me. Circuit dot P gate 3.14 over 2 comma QR of 0, and I can call another circuit dot yeah, Y I called already, okay, P I called, okay, yes, of QR of 0. Then after this I'm going to use only these 4 gates. Then I'm measuring the output. Then circuit dot draw QM MPL. MPL means matplotlib. You can use text also here. Now if I run this code, you will see a circuit like this: X gate, Y gate, B gate, S gate. Let me paste this. I will give few minutes for all of you to get this output. So there are 3 steps: pip install, import, circuit design. Only 3 cells, and you should be able to see this quantum circuit. Can you do this, please? If anyone facing any issue, feel free to unmute yourself and ask the question. If you are comfortable, share your screen. I will fix the issue. This is interesting. I believe you are finding this as interesting. Very good. I believe now you had the confidence that you can do it on your own without referring anything. Right. Now, what you have done, you have designed the circuit. Now, this circuit should be executed on a simulator or QPU, quantum processing unit. But getting access to quantum processing unit is costly because we have to create a cloud account. Some of you may have IBM QisKit cloud account. Now if you want to create, you have to enter your credit card, all those things, then create the account. Whenever you are free, you have free time, do that one. And IBM is giving 10 minutes free access every month. Beyond 10 minutes they will charge $96 per minute. Considering as a learning process, I don't want to spend any money, so I'm going to run a simulator. When I do this pip install QisKit, the simulator is already installed in this notebook instance. So I can create this is QisKit infrastructure. This QisKit -AER. This is the actual simulator. This has a simulator called AER simulator. So I am instantiating AER simulator. So from QisKit _AER import AER simulator, and IBM offers AER simulator, COSM simulator, state vector simulator, density matrix simulator. But mostly we will start with the AER simulator. That is more than enough for learning purpose. If you have any specific reason, then you can go for that particular simulator. Okay. So now I'm instantiating into the sim equal to AER simulator with the shots equal to 1024, and I'm creating a job for run on the simulator, which is job equal to simulator.run the circuit, then result equal to job.result, then output equal to result.get counts. So this get counts method, hello sir, this get counts method will return a Python dictionary. Let me print it. So this 5-line code, 6 lines, right? Yeah, the 6-line code will run your circuit on a AER simulator. Please copy this and paste it. When you run, you will get Python dictionary like this. For this circuit, all of you will get 0 only. But later I am going to change the circuit, then you will get a probabilistic answer. I will stop here. Give 1 minute for all of you to practice this one. Anyone having any question, feel free to stop me, because we are not in a race. We want to learn at least one concept with a clear understanding. That is the success of this session. Aarti told me clearly, KG, this very prestigious audience, we have to make them understand the concept very clearly. Okay, right. Now we got the output. Next, we have to visualize, because a Python dictionary doesn't make sense for end user or client. So we have to visualize it as a histogram. So from QisKit.visualization info plot histogram, and plot histogram the output. When I give this one, it will show the histogram like this, which indicates 1024 times I got the output 0. In the correct quantum terminology, the statement is like this: 1024 times I got the state 0 kit. Is anything mistake? Are you getting? Oh, there is some screen thing is not working correctly. Okay, never mind. You got it right? Everyone got this one right? Now we are going to play around in the same circuit. Sir, can you resend once again that 4th set? Yeah, now you got it right. The from QisKit code. Yes, sir. Balchandra, sir. Cool. There is some delay. I will give 1 more minute for everyone to play around. Then we are going to explore a more exciting part. That will give, wow, this is cool. That aha moment, you will get it. Right? Can we continue? Now, I have to explain the theory part. What is qubit? What is the quantum gates? All those things I have to explain. Before explaining that, I want to show one more behavior. See, these 4 gates are resulting in 0. Correct? That's what you are seeing here. 4 gates are giving 0. But if I add 1 gate here, circuit dot h, qr of 0, what I am doing, the first step I am adding a circuit h. You can see here Hadamard gate, h for Hadamard gate. I added this one. Now I'm executing. Now I'm getting the probabilistic state. A single qubit can be in 2 states, 0 gate, 1 gate. Now I'm getting output. Now it will show these 2 possible states with various probability. You will get different numbers. You won't get 513, 5111. If I run again, I will get different number. That is the nature of quantum programming or quantum simulator execution. All of you are able to do this one. Please make change to your existing circuit by adding Hadamard gate. This line, circuit H. I don't think I need to send it, but still I will send this. That will make your life easier. Okay. Now you started seeing something. Okay, this H gate is doing something to the qubit. The qubit become a superposition. That superposition cause the probabilistic output. Earlier it was deterministic output. Okay, I will stop here and ready to answer your question if any of you have any question before jumping into the next concept. Any question? Right. Some of you, more than 50% of you may feel, KG, this is very, very fundamental. We know this already. If that is the case, please bear with me because we have to cover larger audience. Now I'm going to show some interesting part. Before that, I will give a simple introduction of the quantum state and sorry, sir. Now, when I say qubit, what is come to your mind? Physically, some of you may think about electron, some of you may think about photon, some of you may think about superconducting qubit or ion trap or photonics or neutral atom or D-wave annealer. Some physical system come to your mind. But mathematically, what comes to your mind? I'm not sure how many of you are remembering this sentence. A qubit is, let me add the word, mathematically, a qubit is 2 elements complex column vector. This is what a qubit mathematically. Physically, it may be photon or electron. Physically, a qubit may be any one of the physical platform, hardware platform. Just I will put it, hardware platform, including but not limited to electron, photon, superconducting qubit, trapped ion qubit, like that. It may be many, but we are going to focus on the mathematical part now. If any of you interested, I can explain theoretical part, physics part also, but let us focus on a mathematical part. Why mathematical part? That I can easily connect with this output. So mathematically, when I say 2-element complex column vector, it is this one, 1 plus 0i. This is first element. Second element is 0 plus 0i. In many literature, they will remove this 0i and write it as a 1 0. My kind request, always remember the complex version, don't remember the binary version, because if you see the 1 0, because of our familiarity, we may assume that this is a binary number, but a qubit is not a binary number, it is a complex column vector. Remember that one, because that is going to help a lot when we are doing quantum programming. Okay, with this introduction, and this state is called 0ket, and another state is there which is called 1ket. That 1ket is, okay, let me that 1ket is written like this: 1ket equal to zero plus 0i or I0, whatever you comfortable, and 1 plus 0i. Make sense? Which is written as 0 and 1. Then what will be the superposition? The superposition will be written as a psi-ket. Let me take red color because that is an important concept. Psi-ket equal to 0.707, and it is a very big number, but I am writing only 3 digit, plus 0i and 0 plus 0.707 plus 0i. This is what the psi-ket, the superposition. And in shorthand, it is written as 1 over root 2 1 1, because not everyone can remember this 0.707. So mathematically it is 1 over root 2 1 1. This is what psi-ket. Now with this mathematical intuition for the qubit, now I am going to explain what is a quantum gate. In this circuit, you are seeing H gate, X gate, Y gate, P gate. These are all called quantum gates. These quantum gates are, quantum gate is, let me put the word mathematically. Mathematically, a quantum gate is a square complex matrix. So why it is square and what is the shape, all those things I am going to explain now. For single qubit gate will be 2 by 2 complex matrix, and 2 qubits gate will be 4 by 4 complex matrix, and a 3 qubit gate will be 8 by 8. Now you understood it is a 2 power n. The shape is determined by the number of qubit time 2 power n times. Correct? Remember this one. Why it should be like this? For that I will explain the another segment. So now obviously you may be interested to know what is the matrix for this H gate, X gate, Y gate, P gate, S gate. I remember some of the gates, so I am going to write them from my memory. But later I will tell you how to do that one, how to find the gate matrix for this one. Now, when we start the circuit, the qubit will be in 0 ket, which is written as 1 0. Right? You remember one. You remember this one. Now, what is the first gate I am applying? H gate. So the gates will appear from left to right. But when we try to solve it mathematically, we have to write. We have to draw this matrix from right to left. Correct? So remember this, right? So H gate, the matrix for H gate is, it is a 2 by 2 matrix, as I told you. It is 1 over root 2, 1 over root 2, 1 over root 2, and sorry, I did not use my stylus, minus 1 over root 2. This is for H gate. And next gate is X gate. X gate will have another matrix that will be 0, 1, 1, 0. And next one is Y gate. Y gate, let me write in a different color, a little green color. Y gate will be 0, I, minus I, 0. And next one is P gate. P gate will be 1, 0, 0, e power iota pi by 2, because the 3.14 over 2, it is nothing but pi by 2. Pi by 2. That is P gate. S gate is also similar to this one. I'm not very clear about this one, but I will write it. Later I will show how to do this. 1, 0, 0, e power iota pi. This is also pi by 2 if I am not wrong. Yeah, because this is also pi by 2. Okay. Now, why I am explaining these things, there is a reason. Now we are seeing 5 gates. So since you are coming from digital electronics, you may assume that a quantum computer will solve in 5 clock cycle, correct? But quantum computer won't solve these things in a 5 clock cycle. It will solve all these 5 gates in a single clock cycle. So meaning that actually it will be solved in a single clock cycle. See, till the measurement it is only T0. So we call this as a unitary operation. Unitary operation. That's why to explain that unitary operation only, I draw all these gates. Now you may ask a question, how this 5 matrix multiplication happens the one unitary operation? The secret is matrix composition. Now you will agree with me. Yeah, this is possible. Am I right? You agree with me, everyone? So since these are all compatible matrices, I can compose these 5 matrices into one single matrix and perform the matrix vector multiplication to transform my qubit. So I'm going to type the word because that exact word will help you to recall the correct action. 5 quantum gates are composed into one single complex matrix and performs matrix vector multiplication to transform your qubit. Don't want to add. Does it make sense for everyone? I would like to stop here, answer your questions before going back to the coding. Feel free to stop me and ask the question. Even I encourage you to argue with me, KG, how it is coming. No, it won't work like this. I studied in a different way. You are telling different way. Happy to discuss. A healthy discussion. SNP gate. Oh, okay. SNP gates. Okay. P gate is 100 e power iota theta, whatever phase we are passing. Let me check because S gate I'm little bit confused. So this will happen to everyone, right? Even I'm remembering and then trying to recall, I'm not able to recall the matrix for one gate. So the best way is go to IBM QisKit documentation. I will share that URL also. And here in the documentation, you will see something called API reference. I'm pasting this into the chat window. Where is the chat window? Oops. Here is the chat window. So go to this URL. You will see API reference. Click the API reference. Click this QisKit SDK, Python, C. You see, remember I told you I worked in C++. And now you are seeing yes, QisKit is available as C version also. And click Python. And here go to circuit construction. You will see something called QisKit circuit library. I will wait here. Everyone, please come to this QisKit circuit library. Sometimes some of my mission people will use to comment me, KG, you are making as a LKG students.
Absolutely true, sir. Just you are like holding the how a mother like holding the hands of like the kids, right? You are taking in that way.
Thanks, sir. Thanks for the compliment, sir. I'm taking the positive.
Yeah, but it's really wonderful because, like, academicians, we may not get enough time to learn. We busy with regular academic works as well as nowadays NBA, NAC, NIRF, everything. They are adding lot of documentation works. So
Yes.
we are really, yeah. Hope you can understand. Yes,
Thanks a lot, sir.
thank you, sir.
I hope everyone are here. Here, if you scroll down, you can see the gate, all gates. Now let me see. Go to the first gate, H gate, right? This is the H gate. If you click that one, it will explain. This is a single qubit Hadamard gate. This gate is pi rotation about all the explanation, and it will give this is the syntax. H open bracket close bracket. If you scroll down, it will show the matrix 1/√2 1 1 1 minus 1. But you see, I wrote this as a expanded way because I comfortable seeing this matrix rather than 1/√2 1 1 1 minus 1. It looks simple, but it's not simple. That's why I expanded. And similarly, I can go and then check for P gate. P gate is here phase gate. The spelling is PHASE. It is not just P gate, it is phase gate. So you should become familiar with this terminology, what IBM QisKit is calling. it is 100 e power iota theta. Then similarly, if you go to S gate, and S gate is S gate equal to 100 I, but the I means a pi over 2 radian rotation about Z axis. That's why I wrote e power iota pi by 2. But let us go with what IBM is giving. Let me correct it here. Instead of e power iota pi, I am going to write this as a just I. Most of us will start from X gate and we'll assume that this is a binary matrix, but it's not binary matrix. Now you realizing after seeing Y gate, P gate, S gate, you are realizing that these are all complex matrices. So now hope that answer your question, sir. Some Jayalakshmi madam asked. Got the answer right, madam? Gates are applied from left to right, but the matrices are applied from oppositely. Please explain. Very good question. Now, remember I told matrix times vector. Okay. Now, think about this way mathematically. I am performing this operation. A, B, it is a matrix. A, B, C, D. I am multiplying with X, Y. It is a matrix and vector X and Y. So, what will be the result? It will be, it is 2 by 2 matrix. This is 2 by 1 matrix. The output will be 2 by 1, which will be A time X plus C time Y, B time X plus D time Y. AX plus CY. This is the first element. And BX plus DY. This is the second element. So we are able to perform the matrix multiplication, correct? Now, if I write this way, let me write. If right to left means I have to write like this. X, Y times A, comma, B, comma, C, comma, D. Can you perform a matrix here? Because this one is 1 by 2 matrix, sorry, 2 by 1 matrix. This is 2 by 2 matrix. 2 by 1 matrix cannot be multiplied by 2 by 2 matrix. Mathematically, we cannot perform matrix multiplication. So what we can do perform Kronecker product, which is a different operation. Kronecker product will not transform a qubit. So this operation is not at all possible. That's why we are writing right to left. Hope that answers your question, sir. Krishnamurthy, sir. Okay, right, cool. Now enough theory, let us come back to practical. Now what you have to learn now, okay, there is a transformation. It is really good. We are happy to know that there is a transformation both mathematically, but can we visualize that? Let me show that. Yes, you, oh sorry, not this one. Oh, it is here. This is your code. So to visualize the circuit, you need a few more components. So I'm going to add one more component from QisKit.QuantumInfo import state vector. So a state vector is, I will explain later. For the time being, programmatically you remember the syntax from QisKit.QuantumInfo import state vector. What I'm doing, I'm collecting the state vector of the circuit using SV1 equal to state vector of circuit. Right. So this is a state 1 before doing any operation. After applying Hadamard gate, I am collecting into SV2. After applying X gate, I am collecting in SV3. And Y I don't want to do. After P, I want to collect in the SV4. Then yes, I will leave it. So I have 4 state vector, but after measure you cannot collect state vector. Why? Because the circuit will collapse. to the basis states. But when it is in this mixed state and then superposition or whatever we are before measuring, I want to collect the state vector and then I collected. Now I want to visualize those state vector. Oh, okay, state vector not defined, no problem. Let me run this import state. Not run this one. Now I collected state vector. And even I need not to execute now, but let me complete that execution. This is, you know very well. Now I'm going to visualize that state vector. For that, I have few tools from QisKit.visualization. I will first complete this one and then share the code. Okay. No. I have to share the code and do that one because you can practice along with me. Control C. Then this one I collected state vector, because if you see in your screen you will get more clear understanding. Then after collecting, what I'm doing after execution, now I'm coming here from QisKit dot visualization import array to latex plot multi-vector. That is enough now. Okay, two things I am importing. Now I am displaying array to latex SV1. That will display the column vector in the form of row vector. Don't worry, because that is how IBM array to latex is working. But you visualize this as a column vector. And SV2, you will see after applying Hadamard gate, you will see 1 over root 2, 1 over root 2. And again, it is the nomenclature used by IBM, but mathematically it is equivalent to 1 over root 2, 1 over root 2. And now also it is 1 over 1 over 2. Now I am applying P gate. After applying P gate, you see the P gate is shifting the phase of your qubit. Then the second basis state has some rotation. And first gate become, the negative comes because of the Y gate. If I remove the Y gate, you will see a positive number. Let me share this code such that you can repeat in your system and see those. Sorry. What is that? Yeah. Array to latex will show latex interface that may be easy to understand, or sometimes it may not be easy to understand. That's why I want to show with plot multi-vector of SV1. Now you will see a Bloch pair in 0K. And I want to show fourth state. Not to spend time because you might have figured it out now. Okay, sorry, array to latex. Plot multi-vector of SV4. Now you will see this SV4 is in the some superposition. Actually, it is called -I state. I will paste this code also. You please practice. You try for all state vectors. So this will give you more deep dive into your quantum circuit. I'll stop here. If you have any question, please ask me. I will explain before jumping into the next concept. Next circuit, we are going to see quantum Fourier transform. But I believe this gives a clear understanding of how to visualize your quantum circuit state before measurement. That is an important skill you need to design any new circuit or understand any of the circuit what you get it from internet. Any question? I'll give some time, 1 minute or 2 minutes for you to experiment in your Jupyter notebook, Google Colab. Then ask me if you have any question. I think we have to close by 8 o'clock, right?
Yes, sir.
Array to latex. Array to latex is a IBM QisKit function available in visualization. You see here, if you go to this IBM documentation, here circuit construction, then there is something called results and visualization. If you go here under visualization, you will see lot of way to visualize your circuit. I just to show array to latex and plot Bloch multi-vector, but you have state, city, state, Hinton, distribution, all those things. And array to latex is what it is showing or not. Array latex representation of a complex numpy array within dimension 1 or 2. So this is what a QisKit visualization array to latex method. It will display your qubit state as a latex representation. So, but one thing, it will work only in Jupyter notebook. It will not work if you are running your program as a Py file. Sometimes we will write our program as a Python file, .py extension, and then run it in the command prompt. Those code will not run array to latex. And I would like to share one URL which our organization is maintaining, demo.quantumg.com. This is a free service. You can go here, create your account, and that will give you an experimental capability, or you can experiment with various sorry, you cannot experiment as of now. The code you can copy paste. For example, quantum Fourier transform, you can select this one, it will explain what is the quantum Fourier transform, all those things. Here if you click theory, it will explain the theory. For your information, this program was built by one of the intern from SRM University, Karthiganesh, and one more student from Coimbatore College, KPRIT College, and one student from JPR. So the three students did this project as their internship with our organization. Feel free to explore and understand how these circuits are working, because this will help you. You can understand the circuit, and then you can see here, if you go to the code, you will see the actual code. You can see we implemented this as a class OOPS concept. So, and then the visualization part and all we have written as a code. And when you click the result output, the program will run dynamically, real time, then give the output. Okay. This is really useful because the way how we implemented, it's a pure OOPS concept, object-oriented approach, such that, and it is deployed into our one of our server, cloud-based server. It's not in AWS or it is not in Azure Quantum. It is in a private cloud based out of Germany. So this is a good learning URL. You can learn that one. Now I want to demonstrate you how to, because we have another 30 minutes only. Within this 30 minutes, I'm going to explain how to write a program if someone gives you a circuit. So assume that I have a circuit, Hadamard gate, and CP gate, then Hadamard gate, then swap gate, there we have, then measurement, then another measurement. So this is my first qubit, and this is my second qubit. This is my circuit. Now we have to write a program for this one without referring anything. That is the goal. Now I am going to demonstrate how this circuit is a 2 qubit quantum Fourier transform. This is called 2 qubits quantum Fourier transform. Personally, Fourier transform is my favorite circuit. The reason is that this is the component or building blocks for many other algorithms, be it Shor's algorithm, be it Grover algorithm, be it any other QAOA or any other advanced algorithm. They are using QFT as a building block. And it is a first circuit you should start with Fourier transform. Usually Dijkstra, Benson-Wasserani, Simon algorithm. This is the first thing you have to practice. After that, the quantum Fourier transform, all those things. But Dijkstra is very difficult to explain within 30 minutes. So I selected quantum Fourier transform because all of you know what is the Fourier transform. So I need not explain what is the Fourier transform, all those things. And doing the quantum Fourier transform, you can easily understand, okay, this is transforming one domain to other domain. Here, basis state to quantum phase rotation. That is what it is doing. Let us write a program for this one. Okay. You can take a photo of this one or print screen or do something for the circuit, because the circuit I cannot share in the chat window. Let me continue in the same program, because every time I have to pip install. I don't want to do that one. So I'm going to create a new circuit. QRA equal to quantum register of 2 qubit, comma, I'm calling it as a QFT. Then CRA equal to classical register of 2 qubit CFT, and circuit equal to, instead of circuit I'm putting QFT. The circuit name is QFT. QFT equal to quantum circuit of QRA and CRA. Now QFT dot atom gate to QRA of 1, because I'm applying MSB, most significant bit. So I'm using the index 1. Then QFT dot CP. This one is called CP gate, conditional phase gate, with 5/2 rotation, 5/2 radians rotation. CP2 3.14/2, comma, QRA of 0 get to QRA of 1. Then I have to apply QFT.H for QRA of 0, the first LSB. Then I have to apply swap gate, QFT.swap of QRA of 0, comma, QRA of 1. Now I have to measure QFT.measure QRA, comma, CRA. Then QFT.draw MPL. Shall we draw this one? Wow, we got it. Okay, now I am pasting this. Please practice this one. When you run a QFT circuit, that will increase your confidence. And that is too without referring anything, and just from your memory. If you are typing this program, that is a different level. You start doing this one, you will enjoy quantum programming. Right. And if you want to execute the circuit, you know already. Just I need to repeat this this block. Remember this block as a simrun block. You see the simulator run. So remember simrun. I think it is much easier to remember. So copy this code and run here. Instead of circuit, you should pass QFT, right? And when I run this one, it is giving 11010010, and you can visualize that using plot histogram out. It will show all 4 possible states. Make sense? Now you may be interested, KG, I want to see the state of these 2 things. Obviously, I encourage you to do this one. SV1 equal to state vector of QFT, and after H, okay, let us do only 4 gates, right? SV2 and CP, SV3, after H, SV4, after swap, SV5, SV5. Now, if I run this one, everything will work fine without any difficulty. Plot histogram. Now I am going to show only the BLOS pairs. Plot, BLOS. Okay, let us show array to latex. Array to latex of SV5. I want to show the last element because SV1, SV2, you can figure it out. It is showing 1 by 2, 1 by 2, 1 by 2. At the end, it become 1 by 2, 1 by 2, 1 by 2. What will happen if I do the SV3? So now you are seeing that conditional phase shift is doing something, and SV4 1 1 1 1. Okay, right. Now if you want to plot multi-vector of SV5, you will see two BLOS pairs, both in the different states in the superposition. And visualizing through BLOS pair is not always convenient, so we will use something called QisKit. From QisKit.visualization input plot state QisKit, and I am going to plot state QisKit of SV3 or SV4, whatever I want to display. That will display those two qubits into one single QisKit. This will give you what are the possible states. Now, if I change it to SV4, SV1, you can understand how your quantum system is evolving or transforming at each step. Initially, both qubits are 0, 0 state, but after applying Hadamard gate, you get all possible 4 states. Okay, how come? I applied Hadamard gate only to the MSB. That's why you are getting 2. Then 3. Actually, in QFT 2 qubit, you will not see a lot of differences, but there are some other examples which will show. I usually demonstrate with some other gates depending on the time, but since there is a less time, I follow this QFT. Here, I would like to stop and then share the code. Please play around and ask any question if you are having. Later, I will share this IPy NB file with Thermal Raja sir. Sir will share with you. And also share that PDF of that OneNote. That also will be useful for you because I put that matrix calculations.
Thank you, sir.
Any question? I encourage all of you to ask questions because that is the wonderful exchange of knowledge. Okay. If no more question, I will go back to theory. Is that okay? Okay. I'm assuming it is okay. Let us continue what is happening here. So we are seeing, okay, you understood, okay, KG, there is a matrix, see, there is a vector, qubit is a vector, and quantum gate is a matrix, all are complex number, and then we are performing a matrix composition, and it is performing unitary operation and giving the result. But what is that state vector you used something, right? That is the one important information you have to understand. That is what I am going to explain now. N qubit. Okay. Here is a one question. One thing I want to type for your understanding. N classical bits will be in any one of the possible 2 power n value at any given time. Right? Is that correct? Is that correct? That you know very well. I'm assuming you know, and it is true. But n quantum bits will be in all possible 2 power n states simultaneously. This is what we have to remember. This is a very powerful statement that will explain you why quantum computers are natively parallel. That explains why this makes quantum QC natively parallel. What is the spelling? Natively parallel system. Okay, it's a very simple. Okay, this is one statement you have to remember. Next one is I'm going to explain that natively parallel processing. N qubits. Now you remember n qubits will have 2 power n states. Okay. Since there are in 2 power n state, these n qubits will need state vector will have 2 power n elements. That makes sense because n qubits are having 2 power n possible states. So any state vector which is representing the states of the n qubit will need 2 power n elements. And the state vector is used to represent the pure state. But in between we are going to some processing, right? That time the quantum system will enter something called mixed state. So in the mixed state vector cannot represent, so we will use something called a density matrix. Density matrix will have 2 power n time 2 power n by 2 power n matrix. So you have to remember these statements at any point of time to understand what is happening inside a quantum circuit, or when we run a quantum circuit, what is happening inside a quantum processing unit, QPU. These statements will help you to remember what is happening. I will wait here. If you have any question, I will answer. Then I will show how these things are happening. Any question? We left with the 15 minutes. Okay. I'm going to explain in a different way, Vijayalakshmi madam. That will help you to recall all those things. Okay. Now let us assume I'm going to take 2 qubits. So let us take 2 bits. 2 bits will be 0, 0, 0, 1, 1, 0, 1, 1. These are all the 4 values for 2 bits, correct? And in a digital circuit, if you measure at any point of time, any one of this combination only we can give input or get output. But if you take this as a quantum system, let me use this color. In a quantum system, it will be 0 ket, 0 0 ket and 0 1 ket and 1 0 ket and 1 1 ket. It's not stopping here. Then it looks like classical. You can argue just to put a vertical line and then greater than symbol, you are telling this is a quantum. No, it is not quantum, is not ending here. All these 4 states will be in 25% of this state, 25% of this state, 25% of this state, and 25% of this state. That is the beauty, where a 2 qubit system will be in all possible 4 states simultaneously with probability of 25%, 25% for each state. If I have 3 qubit, it will be 8 states, 12.5% probability. initial state. If I have 4 qubit, it is 16, or no, 100 over 16, that probability. So this probability of the states gives the parallel representation and parallel processing capability. So now the theory, what I have typed with the mathematical representation, easy to understand now. Now I am going to show this practically in a program implementation. I will give 1 minute for any question, then move to the program. You have to understand clearly without any doubt. If you think where suddenly it came, I want to write the popular scikit formula. All of you remember scikit equal to alpha 0 kit plus beta 1 kit. That is what I'm using here. Here I have to use alpha 00 kit, beta 01 kit, gamma 10 kit, delta 11 kit. Instead of that, I'm using alpha 1, alpha 2, alpha 2, alpha 3, alpha 4. So it is my decision. Mathematically, I can use any symbol. I'm using this symbol. That is what the parallel process. Is it okay? Right. Let us move on to the program now. Now I'm going to create another circuit. QRB equal to quantum register of 3 qubit with some Q, and CRB. I don't need CRB. Okay, no, but I need CRB equal to classical register of 3 qubit, put C, and I'm creating QCB, QCB, just any name, quantum circuit of QRB, CRB. Now what I'm doing, SV1 equal to state vector of QCB. Now I'm applying QCB dot Hadamard gate. Oh, sorry, QCB Hadamard gate for QRB. If you just give QRB, it will perform Hadamard gate for all all qubits. Measure. Now I'm just applying Hadamard gate, right? Now let me display the Q sphere of SV1, SV2. Plot state Q sphere SV1. That is expected. The output of SV1, you might expect only one state, 0, 0 state. But after applying Hadamard gate, what is this state? Oh, sorry. Plot state Q sphere of SV2. Now you will see all possible 8 states are present now. Why? Because I have applied 3 qubits, sorry, 3 Hadamard gate. These 3 Hadamard gates make all 3 qubits in a superposition. Then I get alpha 1, alpha 2, alpha 3 to alpha 8 probabilities. That is why it becomes like this. Now imagine that I am removing one Hadamard gate. Okay, let me show that as a 4 qubit instead of 2 qubit. Let me make it as a 4 qubit. Then you will realize this is 4 qubit. Obviously, the Q sphere will show 16 possible states, and 5 qubit 32. Now you are seeing the power of a quantum system which can exist in all 2 power n states simultaneously, which gives the natively parallel processing capability to a quantum computer. I'm stopping here and ready to answer your question. I'm expecting few questions. Okay, both are same, bracket notation or Dirac notation, both are same. This one really a deep question, I think. Very good question, sir. Let me explain. with a physical example. An electron will have a spin, right? The spin can be this way. Assume that the electron is a small magnet and it is N and it is S. Sometimes there is N to S. Sometimes it is S to N. Now assume that I want to represent this magnetic field. So assume that I am having a 2-element vector. The first one gives north, the north spin or up spin. Second one shows south or down spin. So if I put 1 here and then put 0 here, what is the meaning? I have the energy is moving from south to north or up spin. And if I write this vector 0 and 1, it tells south, presence of magnetic field is yes. Or else I can consider, assume that it is a polarity of photon. I can consider the first element is the horizontal polarity, second element as a vertical polarity. So I can write like this, but the scientist, the great scientist Paul Dirac, what he decided, instead of writing like this, let me write a kit like this. This indicates a column vector 1, 0. Why Paul Dirac decided this approach? Sometimes in the processing we will get the broad notation of the same qubit or quantum state. So the bra is nothing but the, where is that one? Yeah. If I write this one, bra 0, it is nothing but a row vector. And it's not just a simple row vector. It is a complex conjugate of kit. So these things will give you a capability. If I perform an inner product, I will get a scalar. If I perform an outer product, I will perform a matrix. That matrix is a density matrix. The scalar is a base. I don't exactly remember what is the scalar purpose, but this obviously, inner product will give you a scalar, outer product will give you a matrix. Most of the quantum systems, when we are enter into the mixed state, they are outer product of all the qubits. So this notation helps the mathematician and scientist to easily represent the quantum mechanical behavior. That is why Paul Dirac used this notation. It is called bracket notation and also called Dirac notation. Bracket notation. So it should be read as 0 ket and bra 0. So when you read ket, the number should come 0 ket, 1 ket, psi ket. When it is in the row vector format, we will say bra 0, bra 1, bra psi, like that. Hope that answered your question, sir. Any specific question, sir? Okay, I think we have another 5 minutes left. I don't want to start any new concept, but I believe this code, even though it is very, very rudimentary, and coupled with these documentation, you can learn on your own at any level, depending on your paper publication or proposal or helping your student projects. These things will be helpful. My kind request, don't go to any ChatGPT or YouTube videos, because they are not compatible with the latest version of QisKit. The video may be older version, that syntax and then behavior might have changed now. So considering that one, always come to this official documentation and choose the correct version of QisKit what you have installed in your system, then read the specific documentation, because IBM QisKit is notorious for version changes and then version incompatibility. That will make your life very difficult if you are searching or looking into some other online source which is related to different QisKit version. You cannot fix it. You can fix only by reading the documentation of the correct version installed in your laptop or server or whatever it is. That is the one thing what practically I found helping me always. And you can also learn Circuit Composer. This is one platform what IBM is giving, easy to design a circuit, and you can design a circuit, get the code here in the QisKit format, then copy paste, run it. Even you need not to write any code for designing any circuit. See, for example, you see the 2 qubit 2 qubit okay, left alignment, so free form alignment, and make it as a conditional fit, and make it as a Hadamard gate and a swap gate and measure operation and another measure operation. You will see the code is here. The code is created here. Whatever code I wrote with a remembering from my memory, typing all those things, struggling, spelling mistake, typing mistake, capital case mistakes. This IBM Circuit Composer will make your life easier, but I strongly recommend stay with hard code method, because big programs cannot be done in this way. But sometimes it is much easier to start, so you can start with this Circuit Composer. But I strongly recommend to use Quniverse.in, which is a CDAC circuit designer. Any proposal if you are submitting to okay, if you are okay, right, entanglement example, okay, right. So if you build a well circuit here, see, for example, actually this CP is your entanglement, but if you put this Hadamard gate and then CX gate, this is entanglement. So when 2 qubits are entanglement, they are connected to each other, or their state is correlated to each other. Any change in one state will affect the state in the other qubit. That is what the quantum entanglement mathematically is represented as the psi1 psi2 equal to 1 over root 2 0 0 ket plus 1 over root 2 1 1 ket. That is the mathematical representation of entanglement. One important thing is entanglement will be always from quantum systems created at source. 2 photons created from the same source, 2 electrons instantiated at the same time. Those quantum systems only can behave with entanglement. We cannot entangle 2 different objects. That's why if you see the QKD or teleportation or super dense coding, you will see the both Alice qubit and Bob qubit are staying together. They are not separate, because it will happen if you use 4 qubit, 2 qubit belongs to Alice, 2 qubit belongs to Bob's. That is how the quantum communication protocols work with the entanglement behavior. Does it answer the question, madam? Is there any specific question, madam? Okay, I'm happy to explain, and then if any of you are interested to connect with me, this is our website, and here you can see our contact details, and then our WhatsApp detail, all those things. I will share this one also, because if any of you interested to upskill yourself, or you have some questions and then inviting me for speech, you can connect with us, and always happy to support and share knowledge. Sir, over to you, sir. I finished.
Thank you so much, sir. Yeah. Really, the way we are you explained is so amazing. You started with using Google Copilot, right? Colab, right? Like from like 1 bit, 1 qubit, and then 2 qubit quantum transformers, and finally 4 qubit the way how you explained it, it's even the professors also like really amazed with your the way you explained. Thank you so much. I think today the research scholars got a very good enlightened session. So really thanks again for your support, sir. Thank you so much. Bye-bye. Thank you. Thank you.
So thank you, sir. Thank you, sir.
Thank you, sir. Bye.